Okay guys, welcome back. We're going to do number 12 from the review packet. And on this one you have a chance to practice the product rule for exponents and the quotient rule for exponents. So when we're working with the product rule, remember that the product rule says if I have a to the m times a to the n, then I can keep my base, and the rule says that I should add up the powers. That's your product rule. Your quotient rule says if you have a to the m over, that's not a good one, over a to the n, then I keep my base again. Notice this only works if the bases match, and in our example they do. Take the top power minus the bottom power, and the order does matter there, so be careful. Now if this had been a nice little problem instead of fractional exponents, we might have had something like x squared times x to the fifth over x to the third. Looking at just the top, I can see that that's the product rule. I have bases that match, and so since I'm multiplying, I can keep my x, and I go this power plus the other power, or I can call that x to the seventh. So that moves us a step closer to being done. The next rule to use is the quotient rule, and that's where I take same base, top power minus bottom power, and the order absolutely matters. So I would say, okay, well then that's the same as x to the 7 minus 3 or 4. But this process that we did, we're about to do with our other exponents. It's a little bit more interesting because of the way we're set up with fractions. If you want to pause the video right now, you could if you're still looking at this one, but I'm going to erase it. Okay, so over here, my product rule says, keep the base, add the powers. So 3 halves plus 3 fifths is what I'm doing up top. Don't even worry about dealing with x to the 5 sevenths just yet. This work requires us, just up in that exponential business, it requires us to get a common denominator. And so I'm going to use a lowest common denominator here of 10. Now if that's the case, maintaining this little guy till I need him. That means I need to say something over 10 plus something over 10. And how would I build that? Well, you have to go back to each fraction and ask, well, what was your denominator and what factor do you need? So I had a 2. I'm going to multiply that by a 5. And that's going to get me a new numerator of 15. Here I had a 5. So to make it into a 10, I have to bring on board a factor of 2 to both top and bottom. So at this point I can say, okay, well I'm getting closer. I've got x to the, let's see, 15 tenths plus 6 tenths gets me 21 tenths. And I still have my 5 sevenths as the power downstairs. And what the rule said is that I should take the top power and subtract the bottom power. And so I'm going to have x to the 21 tenths minus 5 sevenths. Now guys, for these two, what's the LCD for 10 and 7? Well, my LCD would be 70, which is really big. That's okay, we can make this work. I'm going to end up with a problem that looks like this. The powers will be something over 70. And you have to go back and ask yourself, well, if I had 10, what factor do I need to bring on board to make a 70? And I would use 7s and 10s. Okay. Now, 21 times 7 is 147. 5 times 10 is 50. And so you would get, to keep your x, keep your denominator, 147 minus 50 would be 97. And that would be your answer. Okay guys, we're going to take a look at number 15 from your review packet. This one's kind of neat. I love that we get to take a look at this in this course, but we just don't have enough time to play with it. What we're dealing with here is really a binomial squared. We have 2 terms raised to the 2nd power. And the thing you don't want to do is to go ahead and just say 7 squared minus 4i squared. That's not an appropriate usage of that exponent. We're taking the whole binomial and squaring it. So really, what we're supposed to be doing there is not some variation on the power rule, but really we're supposed to be saying, okay, this entire binomial is written in its entirety, however many times the exponent says. The exponent's 2, so we're supposed to write it 7 minus 4i times 7 minus 4i. If you do that expansion, what you find is that you're really looking at FOIL. We have to do multiplying with binomials. So I'm going to go first times first, outside times outside, inside times inside. Now, not surprisingly, these will match. That just happens when we're doing a binomial times itself. And then last times last. Now be careful, a lot of students do this, and I want you to see if you can spot the error. I'm supposed to be saying negative 4i times negative 4i, so that should get me plus 16, and then the I times I should give me I squared. So be careful there. When we do FOIL, we do quite often see that the middle two terms can be combined, and in this case we do find that. We can say 49 minus 56i plus 16i squared. We do have definitions for I that help us move this a little bit farther. We know that I is the square root of negative 1, and we also know that I squared is negative 1. Now this little definition is a helpful piece for us because we know that where the I squared is, we can replace that with its equivalency. We know that I squared is the same as a negative 1. So I can say 49 minus 56i. Now 16 times negative 1 is negative 16. And I want you to notice something. 56i and then 49 minus 16 gets me plus 33. This is what I would call awkward form. It's not necessarily wrong, but we know that what we have really here is a complex number answer. You should always lead with the real part of your complex number and finish with the imaginary part. So I really do prefer, and most tests will have your answer listed in proper form for your complex number. So we're going to go the real 33 minus the imaginary part, the minus 56i. That right there is what we're looking for. We're going to go ahead and take a look at number 22 from your review packet. We're using the quadratic formula to solve this equation. We know that this applies here because remember, one of the hallmarks of a quadratic formula, one that you can use this on, is that the power of 2 needs to exist on your x, and it needs to be your highest power. So we know that it will work here, and what we need to know is how we use the formula properly. Now, there are some things you need to be thinking about. We know that in order to use this formula, which is great, we need to make sure that our equation that we're working on is already in the proper format. Now, our proper format should run ax squared plus bx plus c equals 0. And so I want you to compare this format to what you have. The very first thing you need to do is recognize it's a quadratic and we can use the formula. Second thing is you have to recognize that this is not in the order it's supposed to be in. You need to rearrange it. And so what we see is that we should lead with x squared, we should follow with x, and then your constant term should be next, but it should be on the same side of the equation, and it's not. So we have some work to do. Should always have a 0 on that other side. So we're going to say plus 3 to both sides. This will cancel out, they negate each other because they're additive inverses. And this is awkward form, but I'm putting it there till I have a rewrite moment. So I'm going to say 2x squared plus 6x plus 3 equals 0. So we've got the right format now. And if we've done this, then what we need to do next is we need to get the right information to run through the formula. You need to know little a, little b, and little c. And these are the coefficients of x squared, the x, and then what the constant term is. So in our proper form, we can read these off. So a is just 2, b is 6, and c is 3. The thing that you'll notice is that if you had tried to get those ahead of rearranging the formula or the equation, you would have gotten the 2, you would have gotten the 6, but you would not have gotten the right sign for C. You have to rearrange first. So what we've done is we've made a starter kit that we are going to use to plug into the formula. So I'm going to come over here and do this. If you have trouble remembering the formula, remember you can always put that to a lot of tunes to remember it, but it's always x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So what we're going to do is plug into that. First thing I do is I find b, because I start with the opposite of b, or negative b. If b was 6, that's negative 6, plus or minus the square root. And you'll see when I do this in class, I usually take wherever there used to be a variable, and I put empty parentheses. So b squared minus 4ac all over 2a. I do that to guard myself from making just visual errors where I'm looking at something that really shouldn't be looking the way it does. So we start again with b squared, that was 6, minus 4ac. Now a was 2, c was 3. All over 2 who? 2a, right? And that's another 2 for here. Using the parentheses, make sure that I have the parts in the right place and I have multiplication going on without making sign errors. Now, for me, I usually try to find the quickest, easiest multiplying that I can do, and so I know order of operations requires me to address the square first. Now, 6 squared is 36. And then I have 4 times 2, which is 8. 8 times 3 is 24. And I want you to notice the sign that I ended up with right here. Because I had a minus 4, which always comes with the problem, and no other negative signs in there, then it means that I drop a negative into here. Notice that if this had been a negative 3, then these would have interacted such that I got a plus here. But I didn't. That wasn't there. Therefore, I just have minus 24. All over 2a gets you a 4 down there. So I've taken care of my exponent. That's always first order of business. Taken care of my multiplication. I was mindful of the sign that connects those. And now I go on to the next step. 36 minus 24 is 12, all over 4. A lot of students at this point want to go ahead and start simplifying things, and you can't. Remember that this 12 is not outside of a radical, it's inside of a radical, so it's unapproachable right now. But there is a little bit more we can do. Hopefully you're eyeballing this and you're saying, wait a minute, 4 is a perfect square and it goes into 12. And so we're going to break that up just a little bit more. Using a perfect square factor and what I call the leftovers. The perfect square factor can come out as 2, that's square root of 4. And so I'm really looking at negative 6 plus or minus 2 radical 3 over 4. And I would argue that this is still not quite done. It's almost there, but not quite. If you notice on the top, there's a common factor of 2, and downstairs you also can use a factor of 2 down there as well. So there's a rewrite you can do where you should pull out a 2 from the top 2 terms, which would leave you negative 3 plus the square root of 3. Oh, don't lose your sign. No, it's okay. Pulled out a positive 2. And then if I have 4, then this 2 and this 4 can simplify. 2 goes into 2 once, 2 goes into 4 2 times. And that then would be my final answer. I would have negative 3 plus the square root of 3 over 2. Oh, plus or minus. I lost my double sign. Remember that on the test they may have these listed separately. This really does represent 2 distinct numbers, and I'm going to back up over here to write your answers. It would be negative 3 plus square root of 3 over 2, and then negative 3 minus square root of 3 over 2. 2 distinct, actual, different values. Guys, we're going to take a look at number 29 from your review packet. And what we have here is a system, 2 equations with x's and y's, and they're going to ask us to solve this system. Now you can do this 3 ways. You can graph it, which I know no one's going to do, but you could. You can use the substitution method, or you could use the elimination method. So those are the 3, graphing, substitution, and elimination. And I know some of you become die-hard substitution method people. So I'm going to do it that way first. If I do the substitution method, then you're going to isolate one of your variables. And notice here that you've got negative x, so it's almost alone already anyhow. If I take that and I say, well, let me get x entirely alone. Subtract 4y from both sides. These additive inverses cancel. I get negative x equals negative 4y minus 3. You're almost there, but not quite. You've got to get the x to not have a negative sign in front of it, so we will essentially divide each term by a negative 1. This will give me x equals 4y plus 3, and I always circle that. Now that I'm saying this, I'm saying x is exactly this amount, and if that's true, then I'm allowed to state anywhere there's an x, I can say 4y plus 3. And that's useful because I always tell my students, draw a line into the other equation where the x is, because that right there is where you're going to put in the definition of x. So I'm going to restate this and go, okay, 6 times, not x, we're using what it equals, 4y plus 3 minus 24y equals 5. The only thing I've changed in that second equation is that where there used to be an x, I'm using its definition because we said x is that business. The upside of that, and this is why you substitution people love this, I've just created an equation that's already in just one variable, y is everywhere, no x is left, and now I can just run straight at solving this like we would do in chapter 2. So your first move is the distributive. You go 24y plus 18 minus 24y equals 5. And as soon as I saw that, I went, oh, it's one of those. When we distribute, we properly get coefficients of 24, well, and a constant of 18. In doing this, your next move is to combine like terms, right? So you put your y's together, but when that happens, look guys, those are additive inverses and they're already on the same side, so they negate each other. What I get then is this, 18 equals 5, and now is where you have to say, wait a minute, does that make sense on a Tuesday or Wednesday or any day of the week? If we get 18 equals 5, what that means is you have to interpret what that says about your system. When you get something like this, you need to be asking yourself, is this true or is this false? Because if it gives you a statement of fact, like 18 equals 18, you'd say, yeah, that's true. And what that would mean is that your lines were consistent with each other. It's really the same line. If we get 18 equals 5, which is not true, what that means is that your two lines, they'll never touch each other. And if you have two lines in space, they always touch each other, unless they're parallel. I mean, they don't always touch each other everywhere, but they will eventually touch each other. The only way that that won't happen is if your two lines are parallel. And so when we find 18 equals 5, it means that we have parallel lines, and that in turn means that there is no solution. And that's a valid conclusion, it's just awkward when we land there. If we had had something like this, pretend with me, if we had had 6 equals 6, we would say, oh, that's true, it's true all the time, and that would encourage us to put all real numbers. That's not the case we had, that's just a what if we had that. But if we get 18 equals 5, 18 equals 3, 18 equals 7, in all of those cases, it means the lines were parallel, they'll never touch, and that means there's no solution that exists on both lines at the same time. Now, that's how this plays out for my substitution people, and I know you're not all substitution people, so I'm going to back up. If you want to keep this, then while I stand to the side, pause your screen, like maybe right now. Otherwise, some of you are like, no, why would I do substitution? I want to do it through elimination. And I get that. There's an upside to doing that as well. It's really nice and efficient also. So these are my two equations. Elimination means I'm aiming to get either the x's or the y's rearranged a little bit such that they have additive inverses for their coefficients. So on this first equation, I notice I have a negative x and I have a plus or a positive 6x here. If I take this equation and I multiply it by 6, what happens is I end up with negative 6x plus 24y, you're using the distributive property, equals negative 18. And then if I just bring down that second equation, what I've created quite nicely, and really in just one step, I didn't even have to change both equations. By multiplying this one by 6, I now have additive inverses for the coefficients on my x's, so these cancel. Peculiarly, but not surprisingly, since we already solved this, these cancel, and then do you notice that we also accidentally, but appropriately, created additive inverses there too? Now that doesn't mean there's nothing to write, it means we put 0 equals negative 13, and again, you're asking yourself, is this true or is this false? Well, we know that this is not true, it's false, and again, we draw the same conclusions. We say, well, if it's false, I get 0 that's supposed to be equal to negative 13 and we know it's not, then that means that there is no solution, which would be a point existing on both the first equation and the second equation. I hope this helps. Of course, you could always do method 3 and graph these two, see where they cross. If you do that, you're going to find that they're parallel and they'll never touch. Hope this helps. Have a good day.